Hi everyone, welcome to the 8th weekly live session of the NPTEL course on remote sensing principles and application. This is brought to you by NPTEL and the SWAM initiative. I am Abhishek Chakraborty, a PhD student under the Prime Minister's Research Fellowship Scheme from the Interdisciplinary Center for Water Research at IISc Bangalore. And this course is being tutored by Professor Ishwar Rajshekharan from the Department of Civil Engineering at IIT Bangalore. Just the basic information which I always share before starting the weekly live sessions. First of all, the video recordings of these sessions will be made available on the YouTube channel. The files relevant to the sessions will be made available through a Google Drive folder. I've already uploaded all the documents there already. The files and the video recordings will be made immediately available after the class within an hour approximately. And the images, if taken from the internet, are solely for study purpose. We don't need to intend to use copyrighted work otherwise. So far, we have discussed we have been in 7 other weekly live sessions, and this is going to be the 8th such session. In this session, we are going to exclusively discuss about numerical problems, primarily focusing on microwave remote sensing. So we will be discussing a lot of questions on radar remote sensing primarily. So this will give you an idea about the resolutions of microwave remote sensing, which mind you are very different from optical or infrared remote sensing approaches, which we have learnt a lot so far. We will also learn about the power and transmission characteristics of the range of radar remote sensing approaches, and so we would also be solving a few questions just to understand the concepts. So the first question is that a given SLAR system transmits pulses over a duration of 0.1 microseconds. Find the ground range resolution of the system at a depression angle of 60 degrees. So first of all, SLAR means that it is a side looking airborne radar. So whatever direction it is moving in, which we call it as the azimuth direction, it looks on its side. So that is why it is known as the side looking airborne radar. Side. Anyways, so the question states that the pulses are transmitted over a duration of 0.1 microseconds. Note that the time is so less because it's an electromagnetic radiation, the speeds are massive. Find the ground range resolution of the system at a depression angle of 60 degrees. Let's just firstly plot a schematic of a typical radar system. So this, let us suppose, is a sensor. Let's plot a vertical, and let us suppose this is the target. Let us suppose this dot is basically the target. So the sensor sends up signal to the target and then receives it back. In case it is a active kind of a microwave sensor, we know that very well. So this is something known as the ground range. If you take a direction parallel to the horizontal, then this angle would be something known as the depression angle. And this is what the question has stated to be 60 degrees. Let's take another local normal to the surface. Normal to the surface. That means that this is basically a perpendicular to the localized surface of the target. I'm just giving the definitions right now. So this angle is known as the incidence angle, whereas this angle is also known as the grazing angle. Okay, and this angle, the complementary to the depression angle, is known as a look angle. So with this, I discussed about some common radar imaging terms, and we will be using it consistently in the remaining parts of this weekly live session. So let's try to make similar schematic for the diagram. The depression angle is given as 60 degrees. Okay, just get the sound right. Okay, so the question states that the pulse duration, the time is 0.1 microsecond, means 0.1 into 10 power minus 6 seconds, and the depression angle is 60 degrees. So let's try to plot it just to visualize it better.
Your screen is not seen.
The screen is not visible to you?
No, sir, not visible.
Not at all. Oh my god. Let me try it again then. I hope it's visible now. Is it visible to you now? Hello.
Yes, sir, please continue.
Okay, thanks. So I believe, you could not see the first slide also. So I just, introduced one question, which was uh, about a side-looking airborne radar. It transmits pulses over a duration of zero point 0.1 microseconds, and we have to find the ground range resolution of the system at a depression angle of 60 degree. I also plotted a schematic just to explain the terminologies related to microwave, active microwave remote sensing. So there is a sensor. We basically transmit some signal at the target. It gets returned back to the sensor, and then we sense it, and through that, information about the substance or whatever body we want to detect is finally visualized. Okay, so this is the depression angle, the incidence angle, lookup angle, and the ground range. So the question straight away gives us the depression angle. Let's just make it then. So there is a depression angle in the question which is 60 degree. Let us and this is the ground range. Let us just denote it as R. So if it is 60, this will also be 60, assuming that the land surface is parallel to the lookup plane of the radar system. So what do we get? R cos 60 degree is equal to C times T, that is C is the speed of the time, speed of the light in air, and T is the time duration which is taken. So that is Ct is for one way, and when it returns back, it will be again Ct. So it will basically traverse twice, and that is why we divide it by 2. It is an echoing system. It is very similar to sonar, so that is why we divide it by 2. So let's find out what R is. R is Ct by 2 cos 60 degree. So just put the value. C is 3 into 10 power 8 meter per second. Time was given as 0.1 microseconds. So that is 0.1 into 10 power minus 6 seconds by 2 cos 60 degree, and we get the answer as 30 meters. So this is how we solve this question. Let's move to the next question. Today we will be focusing a lot on the problem solving skills. A radar sends a short pulse of microwave electromagnetic energy directed towards the moon. Some of the energy scatters off the moon's surface and returns to the radar. What is the round trip time? If the target was an aircraft 150 nautical miles of distance, what is the round trip time? Okay, so it's again a very similar question, right? So the first question, part A of the question, wants you to know about the time when it goes to the moon surface. So we've been requiring, time is basically nothing but so speed is equal to distance by time. So time is distance by speed. These questions are very easy in that case. So for the first question, we need to know about the distance from Earth to Moon. That is around 3,84,400 kilometers. So the echoing time, okay, the echoing time would be 2 hour, the total distance traveled by sea. 2 hour because it is traversing from the sensor to the target and back. That is why it is twice the distance. So let's find it out. 2 times 3,84,400 kilometers. We need to convert it into meters by C. C is 3 into 10 power 8 meter per second. So we get the time as 2.5627 seconds. Okay. Now, what is the round trip time that is done for the first case? If the target was an aircraft 150 nautical miles distant, what is the round trip time? So, 1 nautical mile, or in short NMI, is basically 1.852 kilometer. So the T echo in this case would be 2R by C again. So 2R is 1.852 into 150 into 10 power 3. We are converting the kilometers into meters by 3 into 10 power 8. We get the answer as 1.85 milliseconds, means 10 power minus 3 seconds. Let's take another question. A radar transmits a pulse of width of 2 microseconds. What is the closest two targets that can still be resolved by it? So we learned in the class that the closest target distance should again be C times the time of the pulse by 2. This is time of the pulse. So it is 3 into 10 power 8 meter per second times 2 microseconds. So 2 into 10 power minus 6 seconds by 2. So we get the answer as 300 meters. So if the targets are within 300 meters range, then we will not be detect anything distinguishing from that feature. So that is the basic of this question. Next question. The intensity of a transmitted electromagnetic wave at a range of 500 meter from the radar is 0.04 watts per meter square. What is the intensity at 2 kilometer? Okay, this question is very similar to the radiometric principles which we learned earlier in this course. Uh, if we know the intensity at a particular area, we can easily find the intensity at some other area using some inverse square formulation. We know that very well. Okay, so let's try it out. So Ptx by 4 pi r square is equal to watt per meter square. That is given already. Intensity is power by area, and that is what I am doing here basically. So this is already given. So Ptx equal to 4 pi r square times 0.04 watt per meter square equal to 4 pi r. R is 500 meters. So 500 square times 0.04 equal to 4 pi into 10 power 4 watt per meter square. Now that is given, we know the intensity or the power at 500 meter. How do we get to know the intensity at 2 kilometer now? Okay, that's very simple. Inverse square law we have to apply now. Intensity at 2 kilometer would be the power which we found from the previous steps. This is the power into 10 to the power 4 by 4 pi r square, but r in this case is 2 kilometers, that is 2 into 10 to the power 3 meter square. So this would be 4 pi gets cancelled, 10 to the power 4 by 2 into 10 to the power 3 whole square. The answer would be 2.5 milliwatt per meter square. Milli means 10 to the power minus 3. So the answer is 2.5 into 10 to the power minus 3 watts per meter square. Okay. Another question again from radar theory itself. These questions are just to build up your concepts. I believe that the questions from numerical questions from this part, microwave remote sensing, if they come in the exam, they would be very easy. So that is why I am solving these questions also. The fifth question is that find the distance to a radar target in meters for the following round trip delay times. A, it's 12 microseconds. B, it is 120 microseconds. C, it is 1.258 milliseconds. And D, 650 microseconds. Okay. So we are just using that eco concept again and again. Again, that same concept has come in. So distance we want to know. So that would be indirectly the range is equal to T eco times C by 2. Okay. So in the first case, it is 12 into 10 to the power minus 6 seconds times 3 into 10 to the power 8 by 2. Comes out as 1.8 kilometer. The answer would be in meter, but I am converting it to kilometer to report. Second question, we'll just straight away put the values. Eco into C by 2. So it is 120 into 10 to the power minus 6 this time into 3 into 10 to the power 8 by 2, which is equal to 18 kilometer. Because the speed, the time increased by an order of 10, so the range or the distance also increased by an order of 10. The third question, again the same concept. 1.258 milliseconds, so 10 to the power minus 3 into 10 to the power 8 meter per second by 2, that comes out to be 188.7 kilometer, around 10 times more by the way again. And last question, R is again T eco times C by 2, 650 into 10 to the power minus 6, 650 microseconds, 10 to the power minus 6 seconds times 3 into 10 to the power 8 meter per second by 2 again, and that comes out to be 97.5 kilometer. So we are done with this question. It was very straightforward. Find the delay times associated with the following target distances. A, 1 statute mile. Okay. B, 1 kilometer. C, 100 kilometer. D, 250 statute miles. And E, 20 feet. Again, very similar question. We just need to change the units to get into the answers. So let's try it again. Okay, in the fifth question, they were asking the distances. This time we have to find out the times. So I mean nothing huge. Let's do that then. Uh, Two 1 mile is 1.609 kilometers. Statute mile is 1.609 kilometers. So it would be 1609.34 meters by 3 into 10 power 8 meter per seconds. That comes out to be 10.73 microseconds. The answer would be in seconds. I've converted into microseconds just to report. Is again 2r by c. 2 into 1 kilometer. So 1 kilometer is basically b is 1 kilometer. Okay. 10 to power 3 times 3 into 10 power 3 into 10 power 8, that comes out to be 6.67 microseconds. Ct equal to 2r by c, which is 2 into 10 power 5. Okay, 10 power 3 times 100, so 10 power 5 by 3 into 10 power 8. The answer comes out to be 666.67 microseconds. Then the fourth question, t equal to 2r by c, to 250 miles times 1609.34. We're just converting mile into kilometer and then meters. So, and divided by 3 into 10 power 8 again, the answer would come out to be 2.68 milliseconds. And last question in this part, 2r by c, which comes out to be 20 feet, 6.096 meters. 3 into 10 power 8, it comes out to be 40.64 nanoseconds. So we are done with the easy parts. Now let's move into something more complex. So far we have only utilized the concepts of either inverse square law, as in the case of question number 4, or just the speed to distance relationships thanks to eco. And in first question we did some sort of some general trigonometry to understand what would be the range. Now we are into the domain of the Doppler frequency based analysis. Now, uh, usually when we detect, when the observer, let us suppose I have a sensor in my hand and the observer is stationary, then there would be a certain frequency. What if I start moving towards the observer? The frequency will change definitely, and that is thanks to the Doppler effect. So before starting this question, let me just take up some time in explaining what this Doppler effect means, just to build up this concept, especially in the context of radar remote sensing. I also explained a few questions about Doppler effect in probably the weekly live session 1 and 2, probably weekly live session 1, but those were mostly by exploiting the physics part of Doppler effect. This is exclusively for the radar remote sensing. So I would like to take a few slides to dwell into that. So Doppler effect in radar systems. If the target is not stationary, then there will be a change in frequency. of the signal that is transmitted from the radar and that is received by the radar. This effect is known as, this is called Doppler effect. So basically there may be a source, there may be a target. If any one of them is moving, if any one of them is not stationary, then there will be some implications of change in frequency thanks to Doppler effect. And in general, for passive remote sensing systems, in general they active remote sensing microwave systems, in general they are either on spacecrafts or maybe on aircrafts, so they are actually moving. So Doppler effect becomes extremely important in such cases. Let me explain a bit more. Okay, so let's take some simple Doppler effect cases. I would like to discuss this question basically, but for that I need to build up some concepts. The frequency of the received signal will increase when target moves towards the direction of the radar. Okay. Second case, the frequency of the received signal will decrease when the target moves away from the radar. Okay. So let's try to derive the Doppler frequency now, because we know now it is pretty clear, crystal clear, that the frequency will change in case either one of the target or the source uh, is moving. So let's try to derive it. Derivation of Doppler frequency, just a very small derivation. So we call the distance between radar and target as the range in microwave remote sensing terms. Okay, so this implies that total distance in two-way communication. Why two-way communication? Because we send a signal and that signal gets echoed back uh, into the source after being reflected from the target. So it's a two-way communication always. So total distance in that case would be r plus r, that is 2r. Okay, that is equal to signal to target plus again target to signal. The signal and the distance remains the same. Okay. Now, if lambda is, let us suppose it is one wavelength only. If lambda is one wavelength, then number of wavelengths that are present in a two-way communication path between radar and target will be two times the range divided by lambda. Okay, I mean the total distance by wavelength for one cycle. So that is how we will get the total number of wavelengths. We are dividing a distance unit with a distance unit to get the total numbers of wavelengths. Okay. Uh, if there is any doubt, please feel free to interrupt me and ask questions. Anyways, so we know that since one wavelength or lambda corresponds to an angular excursion. This is the wavelength story in in cyclical terms or polar terms. Okay, of 2 pi radians. The phase changes by 2 pi as the wavelength. Wavelength completely finishes. Okay, that we know very well. So this implies total angle of excursion made by electromagnetic wave during the two-way communication path between the radar and target would be 4 pi r by lambda. It was 2 r by lambda, we just multiplied it by 2 pi because in one wavelength it finishes 2 pi. Okay, and that would be in radians. Now we know angular frequency or omega can be written as 2 pi f. F is a linear frequency and omega is the angular frequency. That is how they are related. Okay. Also we know that the angular frequency is related to the phase angle d phi by dt, like this, where phi equal to phase angle. We know that from our concepts of cyclic frequency. Okay, now we just need to equate equation 1 with equation 2, the right hands of equation 1 with that of the right hand of the equation 2. So 2 pi f will be equal to d phi by dt. Okay, let's do that. And through that we will get a very easy term of Doppler frequency. Let's do that firstly. Equation 1 equal to equation 2, so this implies we get 2 phi f equal to d phi by dt. So f is 1 by 2 pi d phi by dt. Let this be equation 3. Now just substitute f as fd, which is the Doppler frequency, and phi equal to 4 pi r by lambda, which we already derived in the previous step. Okay, so this implies fd would be 1 by 2 pi d by dt 4 pi r by lambda. This implies fd is equal to 1 by 2 pi 4 pi by lambda dr by dt. Okay, so through this we get that fd is equal to 2vr by lambda. So if the range is changing, then only Doppler's frequency will come into effect, which is nothing wrong, right? I mean, if there is and this dr by dt is something known as a relative frequency, relative velocity. So there should be a relative velocity between the source and the observer. Okay, they are even if they are both moving, but they are moving at a uniform speed, then also Doppler effect will not be taken into consideration. That's what I want to say. Okay, and fd is something known as the Doppler frequency. This is equation number 4, and this is the most important formula so far. Okay, now let's do something more to this equation. Let's just substitute. We know that Doppler frequency. Let's just substitute lambda equal to c by f, okay, in equation 4. So what do we get out of it? Let's check. So this implies fd is 2vr by c by f. We're just transforming it from the wavelength spectrum into a frequency spectrum. So this gives us that fd is 2vrf by c. So this is the Doppler frequency in terms of frequency of the wave of the electromagnetic spectrum. Okay, now let's come back to the question. If the radar operates at a frequency of 5 gigahertz, then find the Doppler frequency of an aircraft moving at a speed of 100 km per hour. Okay. Okay, so one of them is moving. That is the condition for the Doppler frequency to happen or Doppler effect to happen. So we are given f is 5 gigahertz. Okay, which is 5 into 10 power 9 hertz, by the way. What else are we given? We are also given the relative velocity, which is 100 km per hour. Okay, so this gives Vr is equal to 100 into 10 power 3 by 60 times 60. We are just converting kilometer per hour into meter per second. That comes out to be 27.78 meter per second. Okay, fd, we just put the value in the previous equation which we derived, would be equal to 2vrf by c. So 27.78 times f is 5 gigahertz, 5 into 10 power 9 hertz by 3 into 10 power 8. We get fd as equal to 926 hertz. Okay. So this is the question. Let's take another question now. Another Doppler frequency question. You are traveling 75 miles per hour in a new bright red Ferrari. A nearby policeman using his handheld X band frequency, which is, the frequency of which is 9200 megahertz, speed radar, transmits a CW signal from his radar, which then detects the Doppler shift of the echo from your car. Okay, assume that you are speeding directly towards the speed trap. How many hertz is the frequency of the received signal shifted by the Doppler effect? Is the Doppler shift positive or negative? So they want to know FD again. The question again wants you to know FD. But what is this Doppler shift being positive or negative? This I didn't discuss in the previous part. Let me just give it what it actually means. Speed. We are basically in this question speeding towards his speed trap. That is a sentence given here. Where is this? Yeah, you are speeding directly towards his speed trap. This is what is given. So we are moving towards it. If we are moving towards that observer, okay. So you are moving towards, okay. Then that is known as Doppler shift effect is positive, and vice versa. If you are moving away, then the Doppler shift effect would be negative. So this is just a terminology, and that is what was asked in the last subsection of this question. Okay, now we need to find out the Doppler frequency again. So Fd is equal to 2Vr by lambda. This is the equation, or in terms of frequency 2Vr f by c. So let's find it out then. It is basically, okay, and Vr is 75 miles per hour, which is equal to 120.701 kilometer per hour, or it would be equal to 33.528 meter per second. Okay, so let's substitute in this question. We will get 2 times 33.528 times 9200 megahertz, means 10 to the power 6, okay, divided by 3 into 10 to the power 8. The answer we get is 2.056 hertz. That would be the Doppler frequency. Now, okay, now come the question about azimuth resolution and ground resolution. So let me just give some concepts about it before moving into it. But I would just like to know, is there any doubt so far in whatever I've discussed? I guess no. So I can proceed now. So two very important concepts are ground range resolution and the azimuth resolution. Let me again make that same schematic. This is theta L, look angle. This would be theta D, depression angle. Okay. This is theta D. This is something known as, this part is something known as the ground range, and we are denoting it as RR, R small r. And this part is something known as the slant range resolution. Slant range resolution SR. Okay. Let's suppose T is the pulse duration, then RR or the ground range will be C times T by 2 cos theta D. We did it in the first question, by the way, of today. So it's nothing new to you, but azimuth resolution is something new. So let me discuss that now. Let me denote it as RA. It is by definition the ground distance in the azimuth, and azimuth is basically the direction of the aircraft. Azimuth direction. Okay, so the equation is Ra is equal to Gr times beta. Okay, where Gr is the ground range and beta is the beam width. And beta is related to the wavelength as well as antenna length, as this wavelength by antenna length. Okay, so now just let's straight away jump into the question. A spaceborne radar operating at wavelength 3 centimeter at an altitude 700 kilometer, if the look angle uh, is 30 degree and synthetic aperture length is 1 kilometer, what would be the azimuth resolution of the data obtained? Okay, so firstly, ground range resolution equal to R is C T by 2 cos theta D. Azimuth resolution, which we got from the previous expression, let us suppose it's R is equal to beta times P, where P is the slant range distance. Okay, and P equal to H by cos theta. Okay, where H equal to altitude of platform and theta is the look angle. Okay, so this gives us that R is equal to H beta by cos theta if D equal to the antenna length, lambda is the operating wavelength, and then the antenna beam width is, say, beta is lambda by d. We already did that in the previous expression, wavelength by antenna length. Okay, so combining that, we get the azimuth resolution as equal to R equal to H lambda by d cos theta. This implies R is equal to 700 into 10 power 3 lambda 3 into 10 power minus 2, 3 centimeter it was. Okay, by d is 1 into 10 power 3, 1 kilometer. Aperture length is 1 kilometer times cos theta cos 30 degree. We get the answer as 24 meters. At this moment, I would just like to give a brief summary of whatever we have discussed and some new concepts which would be useful for the next few questions before coming into the uh, radar range equation. So let me just give a brief summary of it before we proceed further. Range is the distance between radar and the target. Okay, so speed equal to distance by time. This, okay, and so distance from it will come as speed by time multiplied by time. So distance is twice because it's propagating the same direction twice, equal to c times t. So this gives r equal to ct by 2. We did that already, by the way. Let's proceed further. Now there is another term known as the pulse repetition frequency. So duration between two clock pulses B should be chosen so that the echo signal is received before next clock pulse. Otherwise, there will be more noise than signal. Clock pulse. Okay. So the time between successive clock pulses is something known as the pulse repetition time equal to TP. So you can visualize it like this. Let us suppose these are the received energy received with respect to the different times. Okay, so any two consecutive crest or troughs, I mean the distance between them, I mean the time distance between them is something but the TP for our case. Similarly, there is another term known as the pulse repetition frequency. FP is the pulse repetition frequency is equal to 1 by TP. Okay. So from it we get to know that we need to, I mean the TP should be at certain range so that we can detect the signal properly. From it we got to know about the from it another concept arises, the maximum unambiguous range, that is the longest range to which a transmitted pulse can travel out to and back again. between consecutive transmitted pulses. Okay, so just substitute in the equation which we derived, substitute R range as range unambiguous un and t is equal to tp. In equation number 1 we will get the term for the unambiguous range as c tp by 2. Very straightforward. Or R unambiguous can be c by 2 times tp, can be written as 1 by fp, which is c by 2 fp. Okay. Now another concept arises, that is minimum range. From this itself, minimum range, R, the range is minimum, and time, just put these values in the equation number 1, we will get that expression straight away. So R minimum is c tau by 2, that is the expression for it. Now let's move into the radar range equations, because all the subsequent questions here are from the radar range equation itself. So let's do that then. Radar range equation. Why do we need that? We need that to know the range of the target theoretically. So I'm underlining this theoretical term because this may not be practical always. Okay. So power density is equal to power by area. Let us denote it like this. PDAI is total transmitted power by area is 4 pi r square. Let us suppose this is equation number 1. PT equal to amount of power transmitted by radar transmitter. Okay. Now one thing we can see is that equation 1 would be valid only for an isotropic antenna. However, radar antennas are not isotropic in nature. One is valid for isotropic antenna, usually radars use directional antennas. Okay, so we need to use a term for that. Okay, so P directional one would be PTG by 4 pi r square, which is G is basically the units of some sort of area. Okay. Now power density, it is also known as a gain, by the way, of echo signal is, let us suppose, PDE equal to PDD times sigma by 4 pi r square. Okay. So PDE is Just multiply it, ETG by 4 pi r square by sigma by 4 pi r square. Now amount of power PR received by radar depends on the effective aperture area, basically, right, of the receiving antenna. So PR is equal to PDE times AE. This is equation number 5. Just substitute the terms, we get PR is equal to PTG by 4 pi r square times sigma by 4 pi r square times AE. So we get R. So these are the two R terms here. Bring it to the left hand side and then take the fourth power, because it is actually R to the power 4. PTG sigma AE by 4 pi square times PR power 1 by 4. Okay. Now this range would be the maximum range when the power is the S-min, that is received echo signal equal to the minimum detectable signal. Okay, so R max in that case would be PT times G sigma AE by 4 pi square times S min. So lower the denominator is, higher the G max would be. Okay. Now G is the gain of directional antenna, and that is 4 pi AE by lambda square. A is the effective aperture. So R max, if we put the term, we get R max is equal to PT sigma AE by 4 pi square S min times 4 pi AE by lambda square power 1 by 4. Okay. Or we can get another expression of R max as PT G sigma AE square by 4 pi lambda square S min to the power 1 by 4. So there can be several ways of writing R max. Depending on what is asked in the question, you can use the given formula for it. Okay. So let's go to the question finally. Calculate the maximum range of radar for the following specifications. Peak power transmitted by the radar is 250 kilowatts. Gain of transmitting antenna is 4000. Okay. Gain is unitless, that we saw clearly. Effective aperture of the receiving antenna, whereas sigma is not. The effective aperture of the receiving antenna is 4 meters square. Radar cross section of the target is 25 square meters, and power of minimum detectable signal means S min is equal to 10 power minus 12 watts. Okay, so we get that PT is 250 kilowatts gain is 4000, aperture area is 4 meter square, sigma is 25 meter square, the radar cross section target, and S min is 10 to the power minus 12 watts. Okay, and we need the, so these are given, and we need the R max. We just put it in the previous equation, PT G sigma AE by 4 pi square S min power 1 by 4. So it comes out as 250 into 10 power 3 times 4000, 25 4 by S min is 10 power minus 12 times power 1 by 4. So R max comes out to be 158 kilometers. Now let's move to question number 11. Calculate the maximum range of radar for the following specifications. Operating frequency is 10 gigahertz. Peak power transmitted by the radar is 400 kilowatts. Effective aperture of the receiving antenna is 5 square meters. Radar cross section of the target is 30 square meters. And power of minimum detectable signal means S min is 10 power minus 10 watts. Okay. So F is 10 hertz. Okay. 10 gigahertz. Okay, operating frequency. PT is given as 400 kilowatts. AE is 5 square meters. Sigma is 30 meter square. S min is 10 to the power minus 10 watts. These are already given in the question. Okay, so let's find out the wavelength first. Operating wavelength is lambda equal to C by F, 3 into 10 power 8 by 10 into 10 power 9, which is 0.03 meters. Okay, yeah, then R max equal to PT sigma AE square by 4 pi lambda square S min power 1 by 4 into 10 power 3 into 30 into 5 square, the aperture area, by 4 pi 0.003, that was the thing here. Okay, square times 10 power minus 10. So what do we get? The answer is 128 kilometers, the maximum range of this radar system. Next question is, for pulse radar with a maximum unambiguous range of 60 km, what is the maximum allowable pulse repetition frequency? Okay, so it's very straightforward. Maximum unambiguous range is C times pulse repetition time by 2, which is C by 2 times pulse repetition frequency. Frequency so 14%. Okay. Okay. So range in this question is given as 60 kilometers already. So PRF, pulse repetition frequency, that's what they want to know, is 3 into 10 power 8 by 2 into 60 into 10 power 3. Okay, so range was equal to C by 2 PRF. So PRF is equal to C by 2 range. And that comes out to be 2500 hertz. Okay. Next question. In a radar system, if the peak transmitted power is increased by a factor of 16 and the antenna diameter is increased by a factor of 2, then the maximum range will increase by what factor? Okay. We know that maximum range of a radar system R max equal to PT sigma AE square by 4 pi square S min power 1 by 4, where S min is the minimum detectable signal power, PT is the peak transmitted power, okay, peak transmitted power, AE is the aperture area, and D is the antenna diameter. So R max can be easily observed to be directly proportional to D to the power 1 by 2 times PT to the power 1 by 4. Okay, so let's just put it into the, put whatever is given into this proportionality equation. So P new is equal to 16p, let us suppose, of old. Okay, D new is 2D, the D old. Okay, so R max we know is directly proportional to D power half and PT to the power 1 by 4. So R new would be square root of D square root of 2 D to the power 1 by 2 2p 1 by 4. Okay, so R new is equal to 2 root 2 R old. Okay, so R new is basically square root 8 times R old. Okay, that is what we get. So the question asks you that maximum range will be increased by what factor? The factor will be square root of 8. 2 root 2 or square root of 8. Okay. Now a couple of a few very simple conceptual questions. Why is microwave remote sensing better suited for monitoring tropical rainforest than optical remote sensing? The reason is that the penetration in tropical rainforest, there is a lot of humidity, and due to that the cloud cover is also huge. The penetration through the cloud cover is not so huge for the optical remote sensing approaches, and that is why most of the signal you want to get is not of the land surface but of the clouds, unfortunately. But microwaves do have a benefit of huge penetration, and that is why microwave remote sensing is better suited. So tropical forest are humid, so cloud cover also huge. Okay, uh, penetration is high through microwave remote sensing. Okay, And that is why, I mean, for such purpose, usually microwave remote sensing is preferred. Then, what is the main difference between radar and optical remote sensing systems like aerial photography or the spot satellite? So, radar is in general an active system. So, it can operate day as well as night. Okay, and it is also insensitive to cloud cover. Whereas optical systems, if they are passive, I mean, mostly optical systems are passive only. They exploit the solar energy which is reflected back from the surface features. And if let us suppose the solar energy is low, if let us suppose a day is primarily uh, primarily it's not a sunny day, or maybe there's a huge cloud cover, then you cannot work. And nighttime coverage is also low because of the same reason. Okay. Next question. Passive microwave remote sensors have a low spatial resolution than comparable, that is same wavelength, same altitude platform active microwave sensors. Why? It's very interesting. Amount of energy reflected or emitted by the earth is very small in the microwave region. Okay, to obtain a signal larger than the noise, we need to ensure that the signal to noise ratio is large than the noise. The signal must be integrated over larger areas, and that basically is the benefit of active sensors. active systems Active systems can produce high energy amounts, whereas passive systems, they do rely on energy from some other sources. What if the energy is low? Then the detection capability will also be low, and that is why the passive microwave remote sensors have a low spatial resolution than that of the active microwave sensors. Okay, we are done for the day, but I would like to wrap up with the assumptions of the radar equation. We discussed about the radar equation so far, but there were some assumptions in that too. The limitations and assumptions. Let's uh, finish today's class by discussing the assumptions of that. Assumptions of radar equation. So the first assumption was there was a free space propagation. That is, the electromagnetic waves travel in straight line from the transmitter to the target and back to receiver without being obstructed by any obstacle. Okay, which is of course a very simplified assumption. Then the the target is point target. The target reflects incoming signal equally in all directions. That is what the second assumption states, but usually that is not the case. So the signal transmission, I mean reflection, may be very discontinuous, non-uniform. That's what I want to say. Number three, there is no interference from other sources of electromagnetic radiation. Okay, but again, I mean, let us suppose you are measuring, you are having a active microwave remote sensing system, and if you are near a transmission power line, your results will be very faulty because there would be some sort of interference. Okay, so the radar equation does not take that into consideration, and finally, it also considers that the environment is homogeneous. So it assumes that there are no variations in the atmospheric conditions or other environmental factors that could affect the radar signal quality. So atmosphere can have variations, in fact, in temperature, density, humidity, pressure, and that can affect the speed and direction of the radar signal, which this equation, of course, does not take into consideration. It is a very simplified equation, by the way. So with this, we are done for the day, I believe.